So I think this is where we left off. We were talking about these are some other types of analyses that we're not going to talk about in here, but they are other things you can do if you have continuous outcomes. So moving forward, what about when you have sort of ordinal or ranked outcomes? What if you don't have continuous outcomes? Most people, a lot of researchers and things will try to force things into a ANOVA or t-test when they're really not supposed to do those things. And there's a whole bunch of these other they're called non-parametric. The reason why they're called non-parametric is because it's considered sort of when you have normal distributions, you have certain parameters like normal distribution. There's certain things that you're assuming. These don't assume those. That's why they're non-parametric. And so you have the sign tests, which in the parentheses is sort of the corresponding parametric test. So a sign test is the non-parametric version of a dependent samples t-test. So if you wanted to compare the same people on some kind of ordinal measure across time, you can do a PrePost on something like order or something like that. Then you can do a sign test. And there's the Wilcoxon rank sum test, sometimes called the Mann-Whitney U, depending on both different ways of looking at an independent samples t-test. And then there's the Kruskal-Wallis test, which is corresponds to an ANOVA. Those are all if you have sort of ordinal or ranked outcomes. If you have discrete outcomes, there's this non-parametric sort of version, which is all the chi-square stuff that we're talking about. But then you also got these other ones that are a little bit more advanced, and they work by sort of converting the outcomes to linear outcomes before sort of making any predictions. Like a logistic regression model uses a logistic function to convert dichotomous outcomes like probabilities into a linear function, predict it, and sort of convert it back. But these aren't things we're going to talk about in here. We're actually not going to talk about any of these things here. It's just, again, these are sort of seeds, things I'm planting in your brain, the things that are either covered places like 100A or these things that exist out there that if you haven't heard of, it's good just to have in the back of your head as you're sort of learning more about these things. All right, so 100A and I think also 100B classes like that sort of spend a lot of time talking about sort of how to deal with data and that kind of stuff. And one of the things that I think students get confused about a lot, and sometimes not even just students, but sometimes faculty as well, is when we talk about distributions, there's things like standard deviation, and then there's sampling error or standard error. So you have standard deviation, standard error, and it's sort of like, well, what's the difference? Aren't they both the same thing? That kind of stuff. So often we use standard deviation as a measure of a distribution spread, but just one distribution. So if I have a single distribution of scores, it'll have a mean, it'll have some standard deviation, right? It'll just have an S. But what if from this distribution, I take a number of little samples like this, right? Take a bunch of little samples, small size, and then I take the means of each of those. This has a mean, right? That's got a mean. That's got a mean. That's got a mean. And I distribute out those means. Now it's still going to have a mean, but oftentimes we refer to this sort of in a different way. It's like the mu sub x bar to make sure that it's like a mean of means. And then how far this distributes out, like it's not going to be a standard deviation like this. It's now a standard deviation that applies to the spread of means instead of the spread of scores. Right, so we're talking about now how means distribute out, not just the individual scores. So when you see like S sub x, or you see something when referring to the standard error, we're talking about how far means spread out when you take multiple samples at a time. And this becomes useful because most of the time what we're trying to figure out is the sample that we have, is that sample that we did something to, we gave them a treatment, we did something to them, are they different than we would expect from the population if we just took random samples? So we need to know how far samples spread out from each other. And that's why we can either sort of manually do this, take a bunch of samples and figure it out, or someone figured out that if we take the standard deviation of one sample, just one individual sample, and divided it by the square root of its sample size, we can directly estimate the standard error and use that. So whenever you see, like, for instance, a t-test, when I do a one sample t-test, it's usually t The t-value is like the mean of your sample minus some population, and it's over that standard error of the mean. So we use this as a measure of how far things spread out to see if we got a sample that's significantly different than other samples. Where just S by itself tells us descriptively about a single sample, it's too big to talk about how far means would spread. I would expect scores to spread out farther than I would expect the means from samples to spread out, because I can get single people that are real extreme, but to get, say, 25 people who are all very extreme is going to be very, 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 very difficult. The probability is going to be very low. So all those samples are going to be really tight around the population mean, and we're going to get a much smaller. Well, how much smaller? Well, about the square root of n smaller. This thing on the bottom, I just like mention this because I think it's funny. This thing on the bottom is called, it has a name. This is called the squashing factor. It's how much a single distribution gets squashed into a distribution of means. Okay. This all sound familiar? I mean, talking about things you never heard about before. Talk to me. What's going on? How's it going? Yeah, you should have definitely have got. I'd imagine everyone, all 100 A's, have gone over this. It's just something that I think even if you got it at the time, it's easy to lose. And you sort of, it's good to sort of revisit and make sure you know what the differences are between like standard error. Because one of the questions in the assignment is, we'll talk about the differences between these three different measures of variability. You got you got two of them, variance and standard deviation, that is a measure that looks at just a single sample, single distribution, where the standard error is actually using that single distribution to estimate how much the means would distribute out if you took multiple samples. Right? So that's the difference between standard error, standard deviation. Standard deviation, one sample; standard error, multiple samples, in order to estimate how much means would spread out if we took multiple samples from the same population. Okay. It's all relative. So the question here is the first thing you asked. I'm just trying to make sure it's on the recording. First question is, if you have a larger standard error that makes your confidence interval bigger, does that mean that you have less confidence? Well, technically, you still have the same 95% confidence. It's just that there's more variability. And remember, the variability is going to be directly tied to the standard deviation of a sample, which also is directly tied to whatever that sample is measured in. So sometimes the width, it's just sort of semantics. Are we talking about gross national product? Well, that's going to be a huge confidence interval because those numbers are going to be gigantic. The standard deviation is going to be in the millions, right? So you're going to have a huge confidence interval, but it could represent a nice, tight, neat confidence interval for that particular value. It's just the numbers we're using are huge. So don't get too caught up in like, well, this distribution has a smaller standard and this one does. Well, it's also measured in a different metric. So that's why we do lots of things like converting things to z-scores and things to standardize things so we can compare across distributions. But the standard error itself doesn't really tell you much, and sometimes it requires you to think about the example we're going to go through in the next set, talking about like smoking and coronary heart disease. You're going to have some standard errors, in terms of how much you're missing in terms of prediction. It's actually called the standard error of measurement, but it's the same idea. It's how off you are in terms of measuring or predicting something, and you have to decide how comfortable you are with that. Because I think in our case, it's like 4 deaths. So it's like whatever we predict for a country, it's like plus or minus 4 deaths. Is 4 deaths okay? Are you okay being wrong by 4 deaths? It sort of depends on what you're talking about. Most people are fine with errors in that way until it comes to things like medical procedures or things where people all of a sudden get very, very uptight about standard errors when it comes to surgeries and things. So it's a long way of saying that the size is sort of relative to whatever you're measuring. So you got to think about it in that context. Are you talking about miles per hour? Are you talking about height? Talking about what are you talking about? And is that a lot for that particular thing you're measuring? There's no real easy way to say like, oh, this is a large or a small standard error, and that is the case for every single measure. It's going to depend. Mhm. Yeah, sure. So we compute a standard deviation, right? It's like how far scores are away from the mean for one sample, for one distribution, a single lonely distribution of scores, right? And for standard error, we've now technically it would be if you took a bunch of samples, hundreds of samples, and now we're looking at their means and how far their means spread across. So standard deviation is the spread of a single sample. Standard error is how far multiple samples would spread. Now you could have a standard error of other things, like you could have a standard error of standard deviation. That sounds crazy, but you can take a standard deviation out of every single sample and see how far the standard deviation spread. But that's not particularly useful. Usually it's a standard error of the mean is what we typically compute because we want to know how far means spread out. And then we can figure out if our particular sample is real way far out there. That's actually how we figure out, like, while we're always talking about tails all the time, right? We have all this represents sort of how far means can spread out, right? We've created a distribution and we know how far on average they can based on that standard error of the mean, right? So we sort of figure out how far this spread is based on that measure. And then we say, okay, well, we know that we know this distribution, and we know that out here there, is this is our 2.5% here and our 2.5% there. If we're talking about a two-tailed test, and I want to know, is my particular sample, I have a sample with a mean, is it sitting out here in the tail? Well, if it is, then it's very unusual. It's not likely to have occurred all by itself out in the wild. We must have done something to it. We must have changed these people by doing things to them, and that's why they're way out here in the tail. And so we say, okay, this is significantly different than the rest of this distribution, and that's why we reject the null and all that whole process. So the whole idea of a standard error is to sort of establish what does a distribution of means look like, and is our mean amongst those means? If not, if it's way out in the tail, then whatever we did to them changed them enough for us to believe that it worked, right? We gave them a drug and it moved them way out there. Well, the drug must have worked, because just randomly varying in this distribution is not a very good explanation for how they got way out there in the tail. That makes sense? So like the whole hypothesis testing steps are all based around this idea of sort of computing distributions of means and then figuring out the standard errors for them. Mm-hmm. Yeah. Yeah. So if I have a, this is the population, right? It's a huge population. This is thousands of, of people in there. And I pull one sample out. Here's my one sample, right? Sample one comes from this population. It's going to have, if we're looking at its, this is its sort of standard deviation. Okay. Oops, it's sort of cut off. Here, I'll just go back at the hue so you can see the whole thing. All right, so it's got, here it is. It's got it's one sample, and I know from that one sample that it's going to have some standard deviation, and we expect that the sample is going to be smaller in terms of spread than the population. All right, so far so good. Well, now if I go back and I take multiple samples, the same size, right? Let's say the n here is, is 10. So all these the same size. They're all going to have their own means. They're all going to be based on 10 subjects, right? So I do this hundreds of times. I'm not going to write that out because it just gets messy. There's hundreds of times. I can now figure out if I want to know how far, if I want to see what the distribution of those means would look like. Right? I want to have a distribution of means. I would know that the mean of all these means should be really close to this one, right? Because the samples may vary a little bit around the population mean, but if I take an average of all of them, it's going to be really, really close to the original population. So that's why we usually call this the mu sub x bar, because it's going to be a close to the population mean. It's going to be based on all these x's. And I'm going to know that how far these things deviate from one another, this S sub X bar, I could do this manually and figure it out, but I also know that this conversion, and when I'm going from a single sample to a sample of means, is going to be smaller by a factor of the square root of n. In this case, because we had our n is 10, whatever S is, S X bar is going to be S divided by the square root of 10. It's going to be whatever that is. Not quite. 3 point something. It's going to be 3 point something smaller. Right? Because that's how much it's going to get squashed. It's going to take one sample standard deviation. It's going to squash it by about a third. Not quite. I mean, a little bit more than a third, but still. Make sense? So you want to think about it visually. Here's my one sample with its one mean and its one standard deviation. All right, so this is how much this spreads out. All right, this is its one standard deviation. Now I have my sample of my distribution of means. I would expect it to be to squish in, right? To be squashed. It should be skinnier because means shouldn't distribute out as far as scores do. So this should get squashed. How much smaller is it going to be? Well, it's going to be square root of n smaller. That's how skinnier it's going to be going from the actual distribution to the distribution of means. Good. So it's why this is the honor sort of follow up. You get to ask these questions like, hey, I never understood this. Well, let's talk about it. Let's figure it out. Remember when I first took at CSUN, the class is 320. That's basically 100A. I remember, I could plug stuff in, I get answers. I didn't really understand what the hell I was doing. I didn't really know why. I just knew, okay, this is what I had to do, and these are the numbers I got to plug in. And I get an answer, and I could explain it. But it wasn't until the next course, which is sort of the corresponding course to this one at CSUN, that I started it sort of make more sense. Started applying it more, started talking more about the details of it. We could take more time to go into a little bit more depth, so it sort of made a little more sense. All right. So now I'm just jumping around a little bit, but going from talking about that sort of standard error and distributions, there's also this whole idea of sort of looking at things bivariately, which is both, I think, talking about both like chi-square and correlation and regression sort of all together. Because the difference between, if you're looking at a chi-square versus a correlation versus regression, it's all sort of semantics, because it's really based on if the variables are discrete, like they're either ordinal or dichotomous or something like that, then you're going to compute a chi-square. But it's still going to tell you how much those two variables are related. If they're continuous, then you're going to compute a correlation, we'll talk about in a second, and it's going to tell you how much those are related, right? Or you can look at how much does one predict the other, but it's actually based still on the same correlation. They're all sort of, it's just different ways of doing the same thing, getting the same answer and using a different sort of method. So I'm not going to go too much into all this stuff because we talk about it in lab, but the basic setup for this stuff, when you do this giant sum, this is observed and expected. So all chi-squares sort of have the same setup. Observed minus expected squared over expected. And the thing about expected is sometimes you're given what the expected is. For instance, with heads and tails, let's say I have a quarter and I want to flip it 50 times and I get 17 heads, 33 tails. Well, I don't have to compute what the expected should be, right? It's not something I need to compute at all. I can simply think, well, if the coin were fair, I would expect 25 here and 25 there. I can use that as my expected. That's it. All right, so I can easily go, it would be like 17 minus 25 squared over 25 plus 33 minus 25 squared over 25. And I would simply add those up and get a chi-square value, right? And I can compare that to a critical value and all that stuff, but then just pointing out that this expected, I didn't compute it. It's just an assumption I made. If a coin is fair, I would expect half heads and half tails. And then this will tell me, is this coin not fair? Because if I got some ridiculous number of tails, maybe it's a weighted coin, like a cheater coin, right? Where you can get more tails come up than heads. Then I can actually tell that by seeing how does it actually differ significantly from what I expect, which is 25 to 25. Now down here, this is a little bit more tricky, because one, we're looking at two variables simultaneously, so it gets a little bit, just to guess at what the expected value should be is a little harder. There's actually, the numbers are made up, but this is actually, like, I think I was in like the 100B equivalent. This is like a study that we did. We literally went out and like watched people coming to a stop sign, and we noted down, obviously the male and female part is based on just visual inspection. We didn't like ask them or anything or talk to them. We just sort of, if they looked like male or female, if we couldn't tell them, we didn't include them. But so male and female, full stop, rolling stop, no stop, to see if there's a difference between genders and how they come to a stop at a stop sign. So we did this, and the way, because of this, it's the same equation, same everything. It's just that the expected values are a little bit trickier to compute. So here I'd have to make another table that's sort of similar in size. Okay, it can be the same thing: males, females, and I need to make then expected frequencies. I could have done that a little better. So I'm going to use this equation here. So here's all, these are the row values, the sides here, right? These are the column values here and here. So to figure out the expected value for this cell, I'm going to take its row value, 23 times 30. Right? So it's going to be 23 times 30 divided by the total, which is 51. What does that give me? 23 times 30 is 690 divided by 51 equals about 13.53. So this is my expected value. Okay. And I would do that for the rest of them, figuring out expected values, and I would go through and follow the same equation to figure out exactly what the chi-square value for this is. And this would tell me whether or not the stopping behavior at stop signs and in this case sex of the driver are related. So it's kind of weird. The chi-square, the names of the tests are oftentimes the null is the name. So if they're independent, it means you would not reject. Right? You're gonna find that they're actually independent from one another. There's no relationship. I think in Jamovi, they actually call it the other way around. They call it the chi-square test of association, which is now the sort of more the alternative hypothesis. Is sex and stopping behavior related, associated? Right. So, but I'm not going to do this just because I don't want to take the time to do it. But this is the sort of process, and we sort of just are going at. But I want you to remember this idea: observed minus expected. This thing, right, is interesting because this comes up a lot. Even though this is chi-square, we talk about observed minus expected. We already talked about something like this before. Whenever we talked about like our xi minus x bar squared, or sum of squares, right? This is really talking about the same thing, because this is my observed value for any individual person. But what would I expect their value to be? Well, I expect their value to be their mean, the group mean. And we do this a lot. So this is an example. It may not be the best example to give you an idea. So for those ladies in the class who are, if you're straight, you date men, and your friends are setting you up on a date, and they tell you nothing about the guy, zero. How tall do you expect them to be? So you know nothing about the person. They tell you nothing about them. But how tall do you expect the person to be when they show up to your door to go on a date? And don't tell me you don't have an expectation, because you're lying. You say you don't have an expectation, because you do. How tall will they be? So if they show up and they're 3'5", are you going to be surprised? Hell yes, right? You're gonna be shocked. You're gonna your mouth's gonna fall on the floor. They show up and they're 7'7", also gonna be completely shocked. So what height are you expecting? About 5'9" ish, right? Somewhere in that ballpark, probably 5'7" to 6 foot, somewhere in there, probably, depending on your given set of friends and acquaintances may adjust that up or down some. But why? Because that is the average height of men. So we tend to expect things to occur at averages. So when we're talking about a sum of squares, we're actually talking about the sum of the square differences between the observed value for a person in a group and the expected value for that person based on their group membership. So it's also an observed minus expected sort of thing at the same time. I'm not going to spend a lot of time talking about correlation and covariance, just sort of fly by those because that's the whole next topic we're going to talk about. So I had it here in the review and I realized that I was going to go into depth with it, sort of left it. So it's here. I mean, the idea behind sort of covariance and what covariance is, it really is just like, think about a variance, which is the deviation between the score and the mean. It's just looking at how two variables are varying together, right? So it's covariance. So we're looking at for each person, their scores on the same on two different variables, how far are they away from the mean? And we're multiplying that. So if you look at the bottom, we're getting, instead of being like the sum of each score minus the mean squared, which is basically just the score minus the mean times the score minus the mean, if I just switch one of these out for a y, right? So I have x and y, two different variables, could be height and weight, whatever you want, right? I could actually switch out this second x for the other variable, the y variable. So instead of a sum of squares on top, what we're getting here becomes, it's now called the sum of products, SP, okay? So two different variables and we're multiplying across. And we'll talk more about this in the next section, so I don't want to spend a whole lot of time. But this is sort of, it's basically the same thing as a correlation. It's telling us how much the variables are related, but it's in its own unique metric. So this is height and weight. Then the end is like, it's like pounds per inch or some weird combination of metric. So we typically will do is try to then standardize this by converting the covariance into a correlation, and all a correlation is just a standardized covariance. So with this has nice restrictions. It can't be lower than -1, can't be higher than 1. If it's close to 0, it means there's no relationship, right? The closer it is to either end, the more related they are. So this is a really nice sort of alternative to covariance when you want to be able to look at the size pretty easily and make judgments about like even multiple relationships to see which things are more related than others. Correlation can help a lot with that, or covariance won't, because covariance, you can have a huge covariance that means a very small relationship, just because you're talking about gross national product again, some big huge numbers, where a correlation gets rid of all that and it standardizes everything, and everything now is between -1 and 1, so it's much easier to compare across multiple things. Okay. Well, again, we're going to talk more about that a lot in the next section. And I'm putting this here mainly because what's the difference between a correlation and regression? Correlation tells you two things are related. Regression tells you if one thing predicts another. There's a direction that gets added. So there's one more piece of information. Instead of just saying, hey, I have X and Y, are they related? I want to know, does X predict Y? It has to be in a particular direction. So you're getting one more piece of information into the process, but it really is doing the same thing, because the correlation tells you how much they're related. I can actually use the correlation to compute the slope. So the correlation here, I can convert that to the slope. So all I'm doing is converting it to, well, what's the covariance? Let me back up a second. This is saying what's the covariance related to the product of the two standard deviations, right? Covariance related to both of them. X and Y related to both X and Y. Or for a slope, it's the same covariance, exactly the same covariance, but now only related to X alone. So we're dividing by the variance of X, not the SX times SY. So it's a slightly different use of covariance that makes it into a slope instead of a correlation, but still really working with this idea of covariance and how much the variation the two variables are sharing with one another. And you've seen this a bunch of times. You've probably seen it in the way we all have, which for whatever reason, I don't know why they teach it as like y equals mx plus b. It's like in high school, that was like how we sort of did it, where m was the slope and b was the intercept. And then we got to mess with you and make b now the slope and a an intercept. There's also the way I actually like to think about it oftentimes is y, because they're both coefficients. I got y equals b1 times x1, so that's the slope that goes with that, plus then b0, where b0 is intercept. So everything's b. Right? All that matters is when you have y equals, you have some predictor, whatever this is here, that's the slope. Whatever this is over this way, that's the intercept. Doesn't matter what it is. Doesn't matter what letters they stick there. Makes no difference. This is the slope because it's right next to the predictor. So because remember the slope, this b, this is a converter. I am converting x units into y units. So this is how I'm converting. This is my converter. And this on this side, this a is just my baseline. Right? So the converter has to multiply with the predictor, and the intercept, the baseline, gets added or subtracted to move it up and down. So this slope makes more or less conversion, makes the slope go up or down. So it tweaks the line, where this one just makes the line go up and down. So it's like two different levers. I have the conversion lever and I have the sort of height lever. I'm just activating them both sort of simultaneously. So don't get, my point of this is don't get hung up on mx plus b or bx plus a or whatever. It doesn't matter. Wherever you learned from wherever you learned it, the thing next to x is the slope. The other thing is the intercept. That's all that matters. And then we have, we start to get in these mixtures of things. So far we had sort of bivariate things. That was the sort of chi-square correlation. Then we start getting into these things where we have both. We have like dichotomous or categorical predictors and then continuous outcomes. And that all started with this idea of sort of doing a z test, a one sample z test. Well, you probably remember sort of z scores, so standardizing scores, taking each score, subtract the mean, divide by standard deviation, turns everything into a standardized z. And then we went a step further and said, okay, well, I can do that. I can take x, this actually really should be x bar. I can take, the sample mean that I have around a population mean, and I can divide that by standard error, standard deviation, standard error. You're probably asking why is it sigma here? Well, this is the whole thing. This is when sigma is known, meaning that the population value is given to you. It actually simplifies things down a lot. You don't have to guess. There's no estimation. It actually is given to you as part of the equation. So if sigma is known and we know the population mean and the population standard deviation, well, I can do a z-test. I can figure out the standard error by taking the population standard deviation and dividing by the same squashing factor. That'll give me my estimate of the standard error based on the population. This is sort of fantasy. I mean, sometimes, every once in a great while, you'll come across, well, this may happen. But if we knew the population values, the mean and standard deviation stuff, we knew that perfectly well, we probably wouldn't do we probably wouldn't be researching it anyway. Like we probably wouldn't be taking samples because we already know it. It's like, working with something like IQ, where IQ is sort of fixed to have a specific mean and standard deviation in the population. We don't do a whole lot of research on trying to figure out what's going on in that population because it's made that way. So in this case, we're able to do lots of things. We're able to create a Z distribution and figure out significance based on the Z distribution and all this stuff. And that's why it sort of started here, but it wasn't very useful. We said, okay, great. Now, what if we don't know sigma? What if we don't know all this stuff? What happens then? Well, now we have to estimate it. And when we estimate it, we know the estimates are not going to be quite right, so we have to do some adjustments. So we created a new distribution called T, where T adjusts for the fact that this thing is smaller. So we know right away that this thing here is smaller than this thing is. We know it's going to be smaller, right? Because it's based on a sample, not the population. So we then adjust T accordingly. Well, how much smaller is this going to be to this? Well, it depends on N, right? The bigger the N is, the closer these two things will be together. the smaller n is, the farther apart these two things are going to be. So t is where the z distribution is a single distribution. It's just one, and we know all the values for it. T is a family. So for every degree of freedom, right, every n minus 1, there's a different t up to a certain point. After about 100, the changes are small. They're in like the 4th decimal place or something. But from 1, which means you have 2 people in the sample, all the way up to like 100, it does change, and we have to figure out it's a whole new distribution for every single degree of freedom. That makes it more complicated, but it's doing this job of sort of adjusting for the fact that these are not going to be sort of exact. These are going to be too small, so the critical values for the t's have to be sort of pushed out a little bit, made a little bit larger to adjust for that. It's sort of like we're taking a handicap or something like that, like play golf or whatever. Like we're sort of adjusting for the fact that we know this is going to be too small. And that's sort of where the t came from. But because this is still a one sample t, the standard error is based on just one sample. So we were able to compute one standard error based on our one sample and compute a t. All right. Well, what if I want to have 2 samples that are dependent? Right? 2 dependent samples. This relates directly to the lab. Right? What if I have two of them? Well, I'm going to have a pre and a post. I have a pre and a post test, which means everybody has 2 scores. Right? Everyone has a pre-test, everyone has a post-test with some kind of intervention in between or something. Well, I can subtract the scores, and that would tell me how much they changed. Right? So if the intervention affected their score, it's going to make it go up or go down. We can actually look at all the differences. So we typically will have like a pre-test, post-test. This doesn't always have to be this way. It could also be brother and sister. They could be related for other reasons. But let's say it's the same people. So this is person number 1. They're going to have some score. Let's say it's 5. They're going to have some score here. Let's say it's 7. Right? They're going to keep going down. This is going to be 6 and a 4 or whatever. And you can keep doing this all the way down to how many people you have. But the most important thing is I can subtract. I can take, say, post minus pre. So post minus pre. And create these different scores. Right? Which is 7 minus 5 is 2, so, is negative 2. I can do that for everybody all the way down, create different scores. And by creating different scores, I can also then get a mean of all the differences. So this x bar d, sometimes you'll see this just written out as just a d with a bar over it, like d bar, the mean of the differences. And why does it say subtracting 0? Why would we do such a dumb thing as subtract 0 in an equation? That's it. Exactly right. Because what is my mu for differences? So that equals 0. I expect there to be no differences on a null hypothesis, because if there's no change pre to post, all the differences should be 0. At least they should average out to 0. So this is not even needed. You oftentimes will see this just written out as the mean of d over the standard error of the mean of d. It should be written that way. T for d is just that. So this is just an implied thing that this is the null hypothesis, right? We figure out, once we have all those differences, we can figure out the standard deviation of those differences. So we can then take the square roots and find a standard error. So this is really just the same thing as the one sample, no difference. Even though it's 2 different measures, it's still one sample. That's why we're able to have just one set of scores, one mean that we compare to a population. Right? So that's pretty straightforward. So even though we're talking about, related samples, things with dependencies, this is actually a lot easier than trying to deal with independent samples. Independent samples are a much bigger pain in the ass, because now we're talking about 2 different sets of people that aren't related. They have their own distribution, they have their own standard deviation, and we're trying to figure out if they're different from one another in some similar way, like in the same way as we did here, but it takes a little bit more work. So why is there more work? Well, now I have sample A versus sample B, and I have two means that I'm trying to figure out. So this is like I have groups come in, let's say it's a drug trial. So let's go back a second. Here, people come in, let's say it's a drug trial. They take a pre-test, I give them the drug, they take a post-test. People are going to say, well, how do you know that the drug really worked and it wasn't expectations that, because they know they're taking a drug, all that kind of stuff. So someone's like, all right, fine, we'll do it a different way. We'll have a bunch of people come in and we'll randomly assign half of them to get placebo and half of them to get an active drug to see if there's a difference that way. That's more of an independent samples test, right? There are two different sets of people getting different treatments, and we want to compare them. So what's unstated here is that technically this difference, same as the one before, it's really also -0, right? The null, right? This mu1 minus mu2, that difference between the populations really is, we're also assuming 0. There is, under no hypothesis, we expect the two groups to be the same, to have no difference, right? So here's where things get messed up. This part's easy, subtract two means, great. But now I got to figure out the standard error of the difference between two means. What? Now I have to roll both samples into the estimate of our standard error, and that's where things get a little tricky. So what we tend to do is we want to average them. So we're assuming that both samples come from the same population. You have to assume that, because or else there's no reason to try to combine them. So if I assume that they're both coming from the same population, then I should be able to average them. Why? Because if I have a giant population like this, and I take one sample, its standard deviation is good. That's a good estimate. And if I have another sample, so this is 1, this is 2, its standard deviation is also a good estimate of the population, right? But both of them together, if I average them, is an even better measure of the population, right? So the more information I have, the better. So if I have two samples, I should just average those two samples together. But what makes it trickier is the sample size. So if one sample is bigger, let's say this is 100, here n equals 100, and here n equals 10, which one do I trust more? Right, we got more people. The 100 is going to be a better, more accurate estimate of the population. So I don't want to completely disregard the 10, but I want to weight this one more. I want to give it more. I want to allow it to contribute more to the estimate. So that's what we weight the variances of each of the samples by their sample size, and then divide by a common standard error. The reason why it's common standard error is because it technically is, this is one standard error, NA minus 1, plus NB minus 1. If I add those two together, that's the common standard error, but it really is NA plus NB minus 2. It's the same, it's just being combined together into one standard error. Add them together. This is also considered big N minus 2, because if I add NA and NB together, that's big N minus 2, because I have two samples, I'm estimating two means, so I lose 2 degrees of freedom. Once I have that pooled value, I can then plug it into here and get the standard error estimate. This whole thing is sort of Pythagorean theorem-esque, right? Because in order to get the standard error, the unsquared version, I'm squaring the standard deviation to get variances, right? And then unsquaring back to get the standard error. So it's like to figure out the missing value, I have to square both, add them together, take the square root. You get the idea. All right, so again, we'll talk about the application of this, like in the lab portion, just a little bit, and sort of talk about where these things are referenced in the output from Jamovi and things, and how going from a one sample test to a dependent to independent to an ANOVA, even we'll talk about all those sort of differences. And I realized I didn't have ANOVA in this thing, because we're going to talk about ANOVA a lot sort of as we go forward, but it's just a different approach to doing. You can actually do the same exact setup through an ANOVA, and you get the same results, because with two groups, if I take the t value and I square it, it's the f value. But those two things are exactly the same with two groups. Once I go to three groups, well, that's not true anymore, because I can't do a t with three groups. Right? But with two groups, I can do a t, but I can also do an f. So that's why they end up being the exact same thing with two groups. And that's what we're going to do in lab to sort of show that those two things are related. They're sort of the same. But I wanted to, we have a little bit of time before we need to switch over. I wanted to start talking about the next thing. I realized I only gave myself 1 day to review, and then I realized we only got through half of it the first day. Or like the second day, and we're already behind. Yeah. It's called what now? Talking about this right here. This is the pooled variance. Oftentimes just referred to as like S squared P. That's the pooled variance. And we use the pool, and the pooled variance is going to come up again because in an ANOVA, we don't have to take the square root. We can actually leave everything in variance because it's analysis of variance. So we can leave everything in variance form. We're going to do this exact same thing again to figure out the variance within groups. We're going to pool them all together. So this S squared pooled in t-test is the same thing as the within groups variance in ANOVA. They're exactly the same thing. It's just this we only have two groups. With ANOVA, I can now have C group, a D group, and I can actually have more groups. And just now it's going to be NA plus NB plus NC plus ND plus NE minus 5. All right, we're just going to be doing more of it. So it's the same, essentially the same thing.